Okay, let us start. Today we will cover a topic which is called screw theory and Lie groups, and basically we will try to understand how can we describe spatial motion. So before we just covered a planar case, so we have used basic trigonometry, right, to describe motion of a planar robot in 2D space. So we had we had only displacement along x and y and rotation around z-axis, and that's it. But in real life, we have not just 3 degrees of motion, right, but 6 degrees of motion, and we can move along x, y, and z, and also we can rotate a body along that x, y, and z. Roll, pitch, and yaw, the angles. And the funny thing is that when we have 3 degrees of freedom, we can take just the time derivative of position, and it will be velocity. But if we'll do the same with the spatial case, it will not be velocity. Velocity will be something else. Velocity will be a little bit different. Why is that? Let us cover something that we already know. Let's assume that we have a plane. So we have a plane, and we have a point right here. It's able to move along x-axis and y-axis. In the case that we covered, we had rigid body, so it also was able to rotate. But right now we will cover just even simpler case, just a point. It does not able to rotate, so it has only 2 degrees of freedom. And in this case, the motion is homogeneous. It means that if we'll take a time derivative, it's like the rate, how fast it's able to change the position, it will be the velocity. But if we will take not just a plane, but a curvature, for example, we can take a sphere like a planet Earth. We also can describe a point with a longitude and longitude, right? So in order to express a point on this curvature, we can use 2 points. But something funny will happen if we will gonna take a time derivative of that. Let's assume that you are right here, and you covered like 1 kilometer, and now you're right here, and everything will be fine. But if we'll do the same kilometer right here, the motion will be a little bit different. I mean, the contribution of this kilometer will be different, because the circle right here will be more narrow, right? And if we go even further to the pole right here, one step, even in 1 meter, will change your coordinates completely. It will be like pi to minus pi. And the time derivative will be infinite of that. And it is called singularity. And in order to get rid of singularity, we can use not 2 equations, not 2 numbers, but 3 numbers, x, y, and z. So it's like we take a space and embed it into another space with the higher dimensions. The same thing will be happen with the description, not just a point with 2 coordinates, but in 3D space. I mean, it's a very simple case, and we can take a drawing, but we cannot draw something in 6 degrees of freedom, because in real life we have 6 degrees of freedom, and we're not going to use 6 numbers, but 16. We're going to use homogeneous transformation matrix. That is matrix 4 by 4, so it has 16 numbers. One row of that is just zeros with a 1, so it has constraints, so not all of them are independent, but still we use more numbers than actually we have degrees of freedom because of this effect. So the disadvantage is that we need to have more numbers, but the advantage is that we can get rid of this problem with the singularity. But at the end of today's lesson, I hope that I will be able to show you. I mean, we don't have a lot of time. Another way to take a look at that, and we will derive a not standard way to describe a motion using exactly 6 numbers to represent the motion. And in this case, we will able to take the time derivative. Okay, so it's like an introduction, the motivation. And another word about the surfaces. Actually, this is something which is called C-space or configuration space. You can imagine a pendulum on a spherical joint, and you can describe each configuration of that pendulum with this representation. For a 2R robot that we already covered, the representation will looks differently. For example, so here I will draw the 2R robot, and in order to represent the configuration of a planar pendulum, I need not a sphere but a circle, right? So by a circle, I can represent each configuration of this link. And I need another circle for the second link. So here I need another circle. And for each Q1, I will have another circle of Q2, right? And if I'll continue my drawing, it will look like a torus, like a donut. So right here you can see a picture of for configuration space, and this is called C-space or topology space or configuration space. And each point on this surface, it's not something in Euclidean space, but it's in joint space, a configuration space. And each point on this donut express the configuration of our robot. So I would like to show you animation. So from here, it's from book of Kevin Lynch that I encourage you to read. And here you can see the animation. So look, if we change Q1, you can see the motion on the donut, and here you can see the motion for the Q2. And now it will be a complex motion. So each configuration of our robot can be expressed as a dot on this C space, which is also called a manifold. So this one is manifold. And homogeneous transformation matrix is nothing else as a manifold to express the configuration of rigid body in 3D space.